Yep. Good evening, everyone. Let's start off. There, last class we started with the conservation of angular momentum, and this was the last thing that we did. Man jumping from the platform, bullet getting stuck to the platform. This is a standard model. Let's see one more like this. Other scans on. Let's say we have a disk here, mass and radius are. This is a point A and this is point B. So AB is the diameter. So we have a person here of mass small m standing at A. Okay, and then what he does, he starts working on the circumference. Right, and reaches point B. So just to show you what happens now, the moment he starts walking, right, the disk won't remain quiet. The disk also will start rotating. If you look at the top view, the picture would look like this. Initially, A was here, B was here, and the man is standing here. Now, when he starts walking, the disk will rotate something like this. A will come here, B will be here. The person who is at A here, now he reached B. So in reality, even though it looks like he's walking 180 degrees, in reality, he walked only how much? He rotated only theta, isn't it? The disk was rotating in this direction. And this guy actually rotated pi minus theta. Is that making sense? If you're walking on the circumference, due to the friction, the disk will rotate in the opposite direction. Find the angle rotated by the disk. Basically, I'm asking you find theta. Now, exam they won't give you this picture. Huh? You have to figure it out on your own. Do you know this problem is looking like what? In center of mass, we remember man walking on a plank. Find displacement of the plank problems. Kind of, it looks like that. But I hope the scenario is clear, everyone. You're walking on the circumference. When you're walking, the B won't be there. B is coming towards you and you're going towards B. So you're actually walking less than 180 degrees. Find the angle rotated by the disk. Let's get this. Hope the question was clear. मेरे आ रही है. Think of like this, huh? Basically, you're replacing mass with moment of inertia, isn't it? What matters is not mass. Listen, now, first thing, since the man is walking on this, the angular momentum about the hinge, right? Angular momentum about that hinge, the center is zero because everyone is at rest. So when this person starts walking, what is angular momentum of the system? Angular momentum of the system is I of the disk, omega of the disk, plus I of the man, omega of the man. The left hand side is zero. Omega will be nothing but d theta by dt. This is d theta disk plus I of the man will be d theta man dt. Dt goes off, and this will be zero. This will be I of the disk delta theta disk plus I of the man delta theta man. Right now, if you try to apply the formula, moment of inertia of the disk is mr square by 2. Theta of the disk, we are assuming this is the picture. So clockwise, the disk is rotating anti-clockwise. So theta minus k cap. The man ka moment of inertia is mr square. He's like a point particle, and he is rotating pi minus theta k cap. So from here we get theta is equal to mr square pi by mr square plus mr square by 2. That would be m pi by m plus m by 2. Check. Clear with this. If you see the formula actually looks like that, right? Planck wala, remember ml by m plus m? It kind of looks like that. So here it was like, the theta will be in moment of inertia, I man pi, whatever is the angle you're rotating, by I man plus I disk. Is that clear, everyone? So L becomes the angular displacement here, so the angle rotated and this thing. And mass becomes theta 1, the moment of inertia. All clear with this? Yeah, that's a decent question. Let's see one more. So let's say we have a small staircase here of height r by 4. We have a solid cylinder, mass m, radius r, which is going with v and omega, and there's no slipping, so we have enough friction. So this cylinder comes and hits the step, and it starts rotating about point A. Think of like this: you're taking a cycle, you're going fast on a cycle, and you're trying to climb a step. So the solid cylinder hits the step and rotates about point A. So it feels like, perfect inelastic collision. It gets stuck. Basically, A becomes like a hinge. It rotates about point A. This is how the diagram would have looked. So it feels, as if A is like a hinge. It is rotating about this. And it has climbed the step. Now, if you go very slowly, you'll hit the step and bounce back. If you go too fast, you'll fly over the step. So there is a minimum speed to climb the step. Find V minimum so that it climbs the step. Hope you got the scenario. You must have done this, right? If you have a small step there and you're going on a cycle, if you go too slow, you won't be able to climb the step. You go too fast, you'll bounce off like a speed breaker kind of thing. But this thing is a little sharp. So basically, it gets stuck about point A, meaning it's a inelastic collision. So you can't conserve energy. Hope the question is clear. Now give it a try. Think it's a good one. I'll give a minute more. Like I keep saying, right? When you see a question, how do you proceed? Step one, okay, does this involve conservations? Does this involve forces? Look at what he is asking. Initially, it is coming with speed V. You want it to climb the step. Means I don't care what is happening in the middle. I just want it to climb the step. So you're more interested in initial and the final position. This is based on conservation. Great. So we figured out it is conservation. Second thing, conservation, meaning you can see, find V minimum to climb the step, meaning you're just interested about the speeds initially. So linear momentum, can I conserve linear momentum? I don't think so, because there'll be a normal reaction here. There is an external force gone. Can I conserve energy? No. E is equal to 0. You can't conserve energy. Angular momentum, that is the only thing left. So that must be the thing. But about which point can I conserve? If you see, torque about A is 0. Just before and just after collision, you can ignore the non-impulsive forces like mg. So I can conserve angular momentum about point A. Start from there. So conserve angular momentum and get omega just after collision. After collision, this will start climbing up. After the collision is over, you can conserve energy. Try. Think. I'll give a minute or two. It's a good one. Let's see. Let's see the first part, okay? So when you're just hitting the step here, if you look at the forces acting on this, there will be a normal reaction, which is passing through the center. There will be also a friction, right? And this is point A. We have mg here. So mg is non-impulse, so we can ignore. So you're just lifting off the ground, okay? You're not touching the floor exactly. You're just about to lift off the ground. So there's a thin gap there. So this is the collision where your pure, the rolling motion converts into pure rotation. So we can ignore this thing. So torque about A is 0. Therefore, angular momentum about A is conserved. Then look at your problem there. This is before collision. This is just after collision. So before collision, you're going with V and omega. After collision, you are rotating omega dash. It has become pure rotation. And here V is equal to R omega. This is point A. So rolling motion has become pure rotation about A. So here A behaves like a hinge, at least till it climbs up. Then initial angular momentum is equal to final angular momentum. This is before collision. This is just after collision. Just after, not too much time. So again, you're calculating angular momentum about A. Initial is equal to final. What is angular momentum? Angular momentum of center of mass plus angular momentum about center of mass. So mv, the perpendicular distance is 3r by 4. The direction, it's rotating anti-clockwise, so minus k cap. I cum omega, which is mr square by 2 omega. It's a cylinder. That is also minus k cap. And then you're rotating about A purely, so this is IA omega dash minus k cap. Minus k cap goes everywhere. This would be, and V is equal to R omega. That would be 3 by 4 plus half, and that's 5 by 4. So this will be 5 mr square omega by 4. Moment of inertia about A, parallaxes theorem, mr square by 2 plus mr square. That will be 3 mr square by 2 omega dash. We get omega dash is equal to mr square goes off. That is 5 by 6 omega. This is the angular velocity just after collision. Since the collision is over, now energy can be conserved after collision. You cannot conserve energy before and after collision, but once the collision is completely done, then you can conserve energy. Any doubt still here? Then comes the second part of the question. Have a look at this page. Then the next part. So collision is done. You got stuck to that point, and then finally you have climbed that step. This is just after collision. Your angular velocity is omega dash. Here omega is 0 because you came to rest. Initially your center of mass is at a height of r. Now your center of mass, this is r, and this is r by 4. Loss in potential energy is equal to gain in kinetic energy. So here your energy will be half IA omega dash square plus mgr. Here it will be mg 5r by 4. So basically all that kinetic energy has become potential energy. Moment of inertia about A is 3mr square by 2. Omega dash will be 5 by 6 omega ka square. And that will be mgr by 4. From here you'll get omega. I will leave it to you. And once you got omega, you'll get omega is equal to v by r. You're done. Other steps clear, everyone? Can you see this thing? Ta-da! Right, Vedika? E0, what happens? In elastic collision, you can't conserve energy. You're sticking to the point A. That is a problem. All clear with this? So, if I have to show you something, not exactly the same thing, but let's see this. Famous scene, Avengers. So they're fighting, all the stuff. Just skip. Thor comes, and there, the main guy comes.
Sir, can you please turn on
If
the
you know
camera?
this scene, so that guy is the Hulk.
Bringing the party to you.
Now see, that is our cylinder. I know it's not a cylinder, but yeah, think of it like that. So that's our block coming. So the cylinder is coming at full speed V. Yeah, it is not rolling, but it is coming with V. This is our obstacle or the step, the Hulk.
That might be able to get time to get in. That's my secret guy. I'm always ready.
Now see, the obstacle is going with full speed, and there. Can you see the scene there? So the step hits the obstacle. And then what happens? It rotates about the obstacle. So it rotates about the Hulk. Can you see how that whole body is rolling over? Can you see how that whole thing is climbing up? So actually, you can conserve angular momentum about Hulk, right? And and during that collision, right, you can see all that energy is being dissipated. It's like a perfectly inelastic collision. You can see how that whole thing rotates. Suppose if this thing was coming very slow, right, this wouldn't have happened. And then see the whole thing goes up. Yeah, this is not in the portion, blasting bombs. So the question got over at that point when it rotates. See, that is the difference between a physics teacher and a normal person who goes to a movie. You see a movie and you think, oh, Hulk is beating stuff. And I was like, oh shit, angular momentum is comes out here. Uh, then, remember I was just talking about the man walking on a plank problem? This is kind of like that. You can see now that there are two people walking now. Just look at the plank. If they rotate that, the whole thing changes direction.
Let the wind.
We want angular momentum conservation. Two people are dancing. So there, you can see the man walks on the plank. And then this is a good video. Right? No, not this one. It is that. Yeah, this one. Everyone should watch this carefully. Yeah, this is good examples are there. I'll post this anyway in the group. There. So we have a student on a turntable. She is holding dumbbells. There. So she's at rest. Kept the dumbbell stretched. So moment of inertia is more, right? And she's rotating. This we have done before. We have seen before. If she brings the dumbbells closer, moment of inertia will decrease, so speed should increase. So just look at her. Look at that. So she's spinning with omega. Brings it closer. Can you clearly see it goes faster? Puts it fast, slows down. I1 omega 1, I2 omega 2. This is a good one, right? Look at this thing, huh? There. Now the girl is standing there, okay, and she's catching that cyclical wheel. She is at rest. Everything is at rest. Look at what happens when she spins the wheel. The moment she spins the wheel, did you observe? She starts rotating in the opposite direction. Now, if she rotates the wheel in the reverse, she will rotate in the other direction. Did you observe that? You can look at that carefully. Initially, everything is at rest. She spins the wheel, she rotates in one direction. She makes the wheel 180 degrees and she rotates in the opposite direction. The girl starts rotating the moment the wheel spins. If she makes the wheel 180, he goes in the other direction. Now she makes it horizontal, she stops. Almost stops. What's happening here exactly? So initially, when the girl was standing with the wheel, what is the angular momentum of the system? Zero. Everything was at rest. The moment she spinned the wheel got an angular momentum I omega. Right? But the girl spinning the wheel is an internal force, isn't it? If the girl spins the wheel with her hand, the system is the girl plus the wheel, so the forces are internal. So to conserve angular momentum, the girl rotates in the opposite direction. Is that making sense? Right? And then when she rotated the wheel 180 degrees, she changed the angular momentum of the wheel. Now she'll rotate in the other direction to compensate. So basically, the angular momentum of the cyclical wheel plus the girl must be always zero. And when she made it like this position, you know why she stopped rotating? The angular momentum direction went from k cap to some I cap, isn't it? In the vertical direction, there's no angular momentum, so the girl stops rotating. So angular momentum in the vertical axis must be conserved. I hope that is making sense. I'll show it on a paper. I'll write down the question also. I'll show you that. But there, this is what he was trying to show. See, left picture, can you see? The whole system is at rest. Middle picture, when the boy that spins the wheel, this wheel rotates in one direction and the whole system rotates in the opposite direction to compensate for the angular momentum. This was the picture. I think it is some Russian language. Now this is a different story. See, the girl is at rest. The teacher spinned the wheel and gave it to the girl. Okay? So when she catches, nothing happens. Now, what is the angular momentum of the system? Angular momentum of the girl plus angular momentum of the wheel. Girl is at rest. Cyclical wheel angular momentum is I omega. Okay? Now see what happens. She rotates the wheel. She starts rotating. Brings it back. She stops rotating. What's happening again? Same thing. Initially, the angular momentum is acting in the upward direction, L, K cap. The moment she spinned the wheel 180 degrees, angular momentum of the wheel became minus L K cap. To conserve the total angular momentum, the girl started rotating in 2L K cap because the total angular momentum is still L K cap. Is that making sense? So whenever you're making the wheel 180 degrees up and down, you're changing the direction of angular momentum. She keeps it horizontal, she rotates. And the best part, see, she stops the wheel. This was the thing. So initially, when the wheel was rotating, angular momentum is L1 upward. When she made the wheel downward, the L1 ka direction became down. But to conserve the total angular momentum, she will rotate in the other direction with L2 upward. So L2 minus L1 is L1. Conservation of angular momentum in the vertical direction. So this is something which you can actually do by sitting in a chair which can rotate. Look at this thing. Same thing, huh? Now, if you just catch the wheel, the girl starts rotating. Did you see? because angular momentum of the system is the angular momentum of the wheel. But the moment the girl stopped the wheel, angular momentum has to go somewhere. So the girl and the wheel together will start rotating. Arya, bolo na, you said something.
Sir, actually, I had a doubt
एक
when
मिनट
she.
रुको, मेरा ऑडियो ये था. बोलो.
Sir, like, actually, I had a doubt when she was holding the wheel, and she was given the wheel by rotating it,
हाँ,
and she turned the wheel in the
180
vertical
degrees.
direction. No, no, not
हाँ,
90 degrees.
90 degrees. हाँ.
Sir, we got a new angular momentum in the this direction, right? Horizontal
वो तो
direction.
फ्लोर पे फ्रिक्शन है ना, वो कॉम्पनसेट करेगा.
Sir, so she actually wants to rotate in this direction.
हाँ, एक्चुअली अगर if the floor had been, if she had been in a gravity free space, कुछ नहीं होता था. She would have rotated in some other direction also.
Okay.
Now in this case, she is restricted to rotate only in the vertical axis ना.
Okay, sir. Sir, so the
हाँ,
normal on that side of the
हाँ, मतलब
platform
जो
will
बोल रहे हो सही
increase.
है. Yeah. So technically speaking, if this had been a gravity free space, ना, the girl would have rotated at some angle. नहीं होता था ऐसा, but yeah. This is the disk wala question, yeah. The disk is rotating with omega. You keep one more disk on top of it. So he's plotting a graph of omega. Friction, it decelerates slowly. Now he keeps one more on top of it. You can see the omega suddenly drops. So this is the disk wala problem. If you keep a disk on another disk, the omega just drops. Because of friction, it is decelerating slowly. So omega does decrease a bit. This is that problem. This is again the man walking on a plank problem. Dekho. Car goes front, wheel goes this side. Car comes back, wheel goes that way. So it rotates the opposite direction. This is that bullet hitting the plank problem. The bullet hits tangential and gets stuck, and the whole plank rotates. So the plank is at rest. The bullet comes with speed u and gets stuck there. This is also a good one. Remember that Versatilium channel ka video I showed you, something similar. So the wheel is rotating. So the L bar is actually rotating in a horizontal direction. If there was no rotation, the wheel would have just fallen down. But gyroscopic precision. Versatilium has made a full video on this thing. If you want, you can check it out for precision. Interesting stuff. But anyway, we don't have it in the portion. There, this was what I was talking about. The angular momentum L bar is rotating, and then you do it. We will do it later, though. I'm going to do a problem on this in advanced revision program. Now we don't need it right now. So there, that was one. That is one. Next thing, there's one more thing I wanted to show. What was this? This is the gyroscopic precision. Yep, I think that's it. Clear with the steps? Then next one. This is another good one. A standard model comes a lot. We have a solid sphere. Ever been to bowling? You must have gone. So in a bowling, what we do? You just throw the ball without any spin, isn't it? You're catching there. So you gave V here, but omega is 0. Then it falls on the rough surface and it starts rolling, and eventually it starts pure rolling. Find the final speed. When it starts pure rolling, or when it stops slipping. So initially there will be slipping. So this is what actually happens when you do bowling. You throw the ball with speed V without any spin. So it slides and then it starts rolling, and it starts pure rolling after some time. So find the final speed when it starts pure rolling. There are two ways to do this. One, we can actually use friction and solve and all. That goes lengthy. But if you use angular momentum, it comes pretty fast. Let me show you this. I'll show you both there is. First, let's do the tougher one. Since you're going with velocity, you're going to skid. You'll have maximum friction because you're skidding, which is mu mg. So you can't take torque about the bottommost point. So torque about center of mass will be F max R is equal to I center of mass alpha, which is mu mg R is equal to 2 by 5 mr square alpha. You will get alpha is equal to 5 mu g by 2r. And similarly, you'll also have a deceleration. So your acceleration will be this way and your alpha will be this way. Be careful, A is not equal to R alpha. You're slipping here. And acceleration will be mu g. So V final will be your velocity initially V minus mu g t. Omega final will be omega initial is 0 alpha t. Eventually, you start pure rolling. So V final will be R omega final. So V minus mu g t is equal to 5 mu g by 2R into RT. We get 2V by 7 mu g. This is how you do with friction. Right? You want to find time, something of this sort. You can even find the time also. I didn't ask you for time, right? I asked you for this, but fine, fair enough. Put the time back and you'll get V final. How much is that? 5V by 7. That's your answer. Clear with this? Now, there's a better way. And this is what I would prefer. Now, if you look at the forces acting on the body here, we have friction, we have normal reaction, and we have mg. So if you take torque about point A, it will be 0. N is equal to mg and friction is passing through A. So torque about any point on the ground is 0 actually. And then mg will cancel. And eventually this will start rolling V final and omega final, and this is point A. So angular momentum about A is conserved. So initial angular momentum, this is what I was telling you. Most people have a problem calculation of angular momentum, right? The problems are manageable, but because you don't know how to calculate your angular momentum, people goof up the signs and everything. How do you calculate angular momentum of the disk? Angular momentum of center of mass, MVR, what is the direction? Minus k cap. We have done this in the last class, right? And there is no initial omega, so I'll ignore that. This will be MV final R minus k cap. Then ICOM omega, it's a solid sphere 2 by 5 mr square. Omega minus k cap. So this will be MVR, so this will be MV final R, plus this will be 2 by 5 MV final R. V final is 5V by 7. You want time, that will be V minus mu GT. You can go reverse, you'll get the time from here. Play with this. But if you just want velocity, angular momentum is the best. You will get it in one step, one conservation of angular momentum, and you're done. Is that clear, everyone? This is the method I would prefer. Arya.
Sir, instead of taking A, we can take it one more step further and.
Bolo.
Sir, instead of taking A, we can take it one more step further and take the point at the very bottom of the sphere.
क्यों मत लेना वो प्रॉब्लम नहीं फिर भी ना द नहीं don't do that उसमें प्रॉब्लम आएगा there is a non-inertial frame. Now let me ask you this, is the point on the sphere or it is on the ground?
Sir, the point is on the sphere after the sphere starts rolling.
But that point is a non-inertial frame. It is accelerating with omega square, centripetal acceleration होगा. And that A won't be at rest ना, तेरा mic और mute में है God.
सर बट इट वोंट मैटर बिकॉज वो वर्टिकल में एक्सेलरेशन है एंड नॉर्मल विल बैलेंस इट आई गेस.
नहीं ना, प्रॉब्लम वो नहीं है. You're in a non-inertial frame. You're conserving angular momentum in the ground frame, and that point is not at rest. Now, if you say this point, after some time, this point is moving here. Means you're conserving angular momentum about different points at different times.
ओ
नहीं,
राइट. पर उससे
it
आंसर
is
तो
not.
आया आई गेस इट्स तुक्का काइंड ऑफ थिंग.
नहीं, तूने क्या किया पता है? You took the point on the ground, which is just below it.
ओके.
That's where it has worked, and that's what I said. Na, any point on the ground would have worked.
हम्म.
देखो ना, initially if you say what was that, if this was A, after some time A would be here, na.
या.
Hmm. So it's basically any point on the ground, it would have worked. All
ओके
clear with
सर.
this? This is a very good model. I'll give you one more. Now you guys try. This question na, comes a lot. Let's see, when I say standard model, understand, you'll be writing two mains exams, two bits exam, two CET exams. I don't know why everything is true too, but still. No, I think I know why it is true too. Basically, they can make more money out of it. Right? That is the main reason. It is not for you guys. Mains फिर भी I can understand. Bits two times is a big blunder. मतलब ठीक है, people say that. You know how much bits earns every year just by conducting an exam? They make almost 40 to 50 CR ka profit. Kidding. Just think about that. One bits application, right, is around 3,000 rupees. But if you apply for both the bits at the same time, you get a discount coupon. You'll get it for 5,000 rupees. So if you apply for bits 1 and 2 together, you get for 5,000 rupees. If you apply them separately, you get 3,000 each. Okay, let's assume 3,000 rupees. And how many people write the bits exam? More than a lakh? A lot of people write the exam, right? So if you assume even 1.5 lakh people are writing the exam, 1.5 lakh into 3,000, how much is that? That is for one exam. By putting a second exam, let's say second exam only 50,000 people are giving. How much is 50,000 into 3,000? And how much does it actually cost to conduct an exam? It costs you around 600 rupees to 400 to 600 rupees. So out of 3,000 rupees, even if you assume 1,000 rupees is gone, they're making profit of 2,000 rupees per kid per exam. And if 2 lakh people write the exam, that's a profit of 40 crores without doing a single thing. Not teaching, no infrastructure, no faculty hiring, no material, nothing. 40 crores pure profit. That's what you can do. Right? So, Chana, mains exam, they'll conduct it for 1,000 rupees. Bits exam is 3,000 rupees. So people realize this. So it works out. It's a good startup idea, yeah. But for that, you need to have a reputation for your institute, right? If you open some Don Bosco, Institute of Engineering ka entrance exam, no one is going to come and write it. So anyways, yeah, now it is exam season, na? I think last week only BITS ka notification came out. This time they're conducting one in April and one in May 24th. May 17th is your advanced exam. Next week they're conducting the BITS exam. Normally, BITS exam used to be on May 2nd week and June 2nd week. They shifted it 1 month. So paper making kuch nahi hai. Online questions, how long does it take? You have a question bank, the computer just takes from there and prints it up. You just need to make the question bank once. You can use it for a decade. And BITS ka questions don't come out, so you don't even know what shit question they're asking. They never release the paper. Cool, right? BITS ka bada problem wahi hai. Outside there is no proper material, to solve actually. This is V. This is omega with 3V by R. Find V final, omega final, and time when stop slipping. What do you guys think mains papers are made by humans? Those days are gone long back. Questions do repeat a lot. That is the reason we keep telling. So last 5 years ka PYQs properly from mains. At least 4 questions will repeat. 3 to 4. So let's get this. So this is a very standard model, comes a lot in different exams. 4V by 3 mu G. Okay. Well, that's fine. Hmm. You know how can you get this kind of velocity? Uh, when you play caroms, next time you can try like this. Take a coin, put it vertically like this, put your finger on top of this, and then press it hard. Did you ever do this? When you're bad in caroms and you don't know how to play, you do all this kind of shit things on the game. Right? Right? You ever did this thing? If you push like this, right, with a finger, the coin goes front. So what you're doing, you're giving omega in the reverse direction, but V forward. The coin keeps going forward and then it comes back again. Ever did this? Yeah, you should. That's what I'm saying, You want to learn physics, these kind of weird things you have to do more. It goes front and comes back. If you have ever try that. I used to play with my friends in IIT though. We used to do all these kind of things. I used to hide coins also. People used to be like, what the hell happened to the coins? People used to be scared of playing caroms with me though.
Why,
Yeah,
sir?
just like that. They used to call me the destroyer. I used to come and just smash the board right and left. The coins used to fly everywhere. Yeah, in the beginning, I used to play very good actually. I used to play properly, but then what happened? No, people started becoming very competitive. वो होता है IIT में that I observed. You play something right. Initially, they play for fun, and then after a week or two, people suddenly become very competitive about it. And then it became very serious actually. People are literally like, they're playing as if something like I said, like, what bullshit is this? Then I stopped playing seriously, I started doing all nonsense.
So, but what do you mean smash the board?
Eh, matlab, see, for example, match the board means nothing. There's a coin here, sure coin, right? Normally what you do, you play properly. नहीं हम ऐसा नहीं करेंगे. We will hit it so hard, this will fly out and this coin will fly out. Some coin will go and fall here. Anything happens on the board. So the next person, right, who was thinking, okay, I will play this, I will play this, his entire strategy is messed up. Now that guy has no idea what the hell is going to happen. My own teammates used to get pissed off like, boss, why the hell did you do that? So they used to pair me up always with the one of the strongest players. So in our college, that my teammate, there is one guy called Harish. He was very good in caroms. That guy used to feel he's playing 1-on-3. They used to feel like, Arun, are you in my team or in their team? I said, doesn't matter. I'm a third player there. I used to tell them that only. I am the chaos. Like it doesn't matter which team I am. I'm going to just beat the coins right and left. It was fun.
So
Nee,
that's what happens. They cracked IITJ and they become too competitive.
people become really competitive. मैंने वो बहुत देखा था that thing. For every damn thing they become competitive. Why all that? I remember in my second year, we had summer holidays. Okay, we stayed back for a project. This was 2007-8 का बात था. So right now, remember on your phones you have all these games, na? क्या था वो game? I don't remember. You have your small village, you build your army, you go and attack the other people and all.
Clash of
You have
Clans.
games. Clash of Clans. So people know all that, huh? तो वही है. तो Clash of Clans. So 2007 and 8 का time में there is a game called Tribal Wars. That was the first game of this Clash of Clans का you can ancient ancestor. Getting it? That was a game of Tribal Wars करके. So someone founded the game and we all started playing the game. Right? इतना competitive हो गया था मतलब right I started doing all nonsense. I created 130 accounts. Right, I had 130 accounts. I had literally full continent under my control. So I and four of my friends we were playing 130 accounts in that. अकाउंट का नाम भी हाईलाइट था सुपर गोट 1 सुपर गोट 2 सुपर गोट 3 सुपर गोट 40 सुपर पिग 1 सुपर पिग 2 सुपर पिग 40 right. So we had ऐसा 130 accounts and actually that was how we got caught actually because the names are so repetitive. They found out 130 accounts. So there was a big game, in the world ka top 10 mein we are 9 accounts are ours only. We were literally decimating everyone. Can you imagine? Like, we used to, calculate the calculations, how to attack the enemy, how should, armies go one after another. So there was one guy, we are literally planning to write a code on how to write, break those things and stuff. We played the game almost for I think 1.5 months. People were putting alarm clocks in the morning. 3:30 we used to keep an alarm clock, wake up, and then used to put all the account data and then sleep again. We are playing so seriously as if something, the world depends on us. And then finally, we decimated almost, I think half the players got decimated by us. We are just smashing everyone. And then someone reported us. Wow, these people are cheating. They're having so many accounts and all. Meaning, just imagine you're an enemy player and suddenly you get an attack. Super God 1 is attacking. You think, okay. Super God 2 is attacking. I said, okay. Super God 3, 4, 5, 40 is attacking. Then you think, like, what the hell is this Super God? Then you see Super Pig is coming to attack you. It used to be fun. It was really fun. We played almost for a month. It was so competitive. And then they banned the entire IIT Madras ka IP code. So IP server entire IIT Madras was banned from playing that game. And that the guy, whoever is the moderator, he wrote a mail to me. You guys have created so many accounts, which is not right. It is against the game ka rules, blah blah blah. But I must say, I'm impressed with your tenacity to maintain 130 bloody accounts. So that guy was praising us. We felt good. Yeah, after that, we never played that game. It was too much actually. We couldn't sleep, we couldn't eat properly. We were running like mad. Four of us were playing 130 accounts. Just because we want to be in that World Cup top 10. We wanted one account. We had 9 accounts in top 10. So there. That's the problem. वो होता है, बहुत होता है. People become really competitive. The fun goes off. Then you need someone like me to come and balance again. Anyway, so it's a good place to be, but
Smash.
smash. Yeah, we used to play football also. No, I am very bad at football. So I wanted to play like that. So they made me the goalkeeper. The ball never comes. If it comes, that come once in a while, and I'm sleeping exactly at that time, and the ball goes inside, and people start shouting on me. So I got so pissed off. Then I started building, a barricade in front of this thing with stones. I was bored. No one is looking at me. The guy came, tripped on the stones, and fell down. I saved the ball from goal. They removed it from the game. I got so pissed off. I went to the second floor. I bought buckets of water and started pouring it on people from the top. And these people started chasing me with hockey bats. So we changed the whole game. It was fun. So I was caught anyway. Then they started catching me and started beating me with bumps. So right? They catch you hands and legs, they make you float in there, and then they beat you from the bottoms. So yeah. Anyway, so look at this thing. So we have your initial situation, the final situation. If you look at the forces, that is the fun of staying in the hostel. Did you ever play, football morning 3 o'clock when it is raining? We have hostels with floodlights. You can switch on the lights, entire ground is lit. Morning 3 o'clock. People are playing football, people are playing rugby, it is raining, people do anything. So if you look at this again, same story, we can talk about point A is 0. In this case, actually friction would be back only. So I can conserve angular momentum about A. Be careful with the signs. What is initial angular momentum? MVR minus K cap. It's a disk, so it is MR square by 2. I think I should have taken a solid sphere. Previous one was already solid sphere. No? Take a disk is fine. MR square by 2 omega, which is plus K cap. So that's what I'm saying. Blindly just don't add up everything. You have to be careful with the signs. This is MV final R minus K cap. MR square by 2 omega final minus K cap. You got everything. Substitute here. This would be minus MVR plus R omega is 3V. So this is 3 MRV. This is MV final R minus MV final R by 2. You're getting a minus sign. V final is equal to minus 4V by 3. I got 4V by 3. Anyone else got that? Did I mess up somewhere? Looks right. Check. I think you guys got V by 3, I guess. Looks like I messed up somewhere. MR square by 2 omega. There is a 2 sitting here. Then this will be MR V by 2. This is a V by 3. Perfect. Clear with this. So we thought it is going forward. That's what I'm saying. It doesn't matter. The sign will take care of it. This is actually going back. You can try this with a carom board coin and say it works. So if you give spin back and you throw it forward, it is going to come back. And then what else you need? I think you'll get everything from here. You want time, so friction will be mu mg. So acceleration will be mu g. So V final will be V minus mu gt, but your V final itself is minus V by 3. So time will be 4V by 3 mu g. You got everything. Please have a look at this. Any doubts on this? Clear with this? Take a break. Come back in 5 minutes. We'll continue from here. Any doubts so far? So come back in 5 minutes then. Chalo, let's start. Now, this next model of questions, right? These are important collision problems. Top view. So let's say you're keeping a rod on a floor, mass M, length L. And we have a ball of mass M here, which is going with speed U. It hits the end of the rod. Coefficient of restitution is E. Remember, this is on a smooth floor, okay? So there is no gravity. We'll do one problem with all variables, and we'll put some numbers. So first thing, find velocity of the rod, omega of the rod, velocity of the ball after collision.
Sir, can you please give capital M in terms of small?
Nah, capital M is M only. Get me the answer in capital M. Just write the equation and leave it if that's the problem. Find the point on the rod. You will need that, right? Because I can ask multiple questions like this. Find the ratio of M by small m if the ball stops after collision. So you can play a lot by keeping variables. Find the point on the rod whose velocity is 0 just after collision. Remember, if on a rod you can find a 0 velocity, it is your IAR. There, try. I'll give 3 minutes. At least let's get the equations. Then I'll show you one model how to handle this, and then I'll give you more on this. So listen, how do you handle these kind of problems? Step one, draw the final picture. One thing is clear. We can't do this with forces and stuff. So we have to use conservation. This is your before collision. This is at rest. So after collision, let the rod go with V2. Let the omega be backward, and let the ball go with V1. So basically I have three variables, V1, V2, and omega. So if I know these three, my job's done. And V2 is nothing but the velocity of center of mass of the rod. Perfect. This is after collision. Step 1. Are there any external force on the system? No. So I can conserve linear momentum. Initial momentum is mu. Final momentum is mv1 plus mv2. This is equation 1. That was straightforward. Step 2. Coefficient of restitution. Now here be careful. When you write restitution, when you say E is equal to V2 bar minus V1 bar by U1 minus U2 bar, these are velocities of exactly what? These are velocities of point of collision, isn't it? Till now, we never had a problem because we treated them as point objects. These are velocities of the point of collision. This is not the velocity of the center of masses. That means when you take the velocity, you should take actually velocity of this point of collision, which is V2 plus L by 2 omega. So now when you write restitution, E is equal to V2 minus V1. This will be V2 plus L omega by 2. That is the velocity of the point which you are colliding, minus V1 by U1 minus U2, which is U minus 0. Are you clear with this? This is the velocity of that bottommost point on rod. This is your equation 2. Is that clear, everyone? So your V2 minus V1 is not velocity of center of masses. It is a point of collision. This is your step 2. Step 3. You can't conserve energy here because E is not equal to 1. I said E, so there could be an energy loss. Conservation of angular momentum. Now, about which point? Technically, you can take angular momentum about any point because torque about every axis is 0. Torque about any axis is 0. Therefore, L bar about any axis is conserved. So just for sake of calculation, I will do two things. Okay, first I'll do about center of mass, then I'll do about point of collision. I like the point of collision, but let's do about each one. Angular momentum about center of mass of the rod or center. So we have the rod, we have the ball, we have the rod, we have initial angular momentum, we have final angular. I'm just making a small table. So what is initial angular momentum of the ball? So you're talking about this center. Drop the perpendicular distance mu L by 2. Direction would be upward, k cap. Final angular momentum of the ball mv1 L by 2 k cap. Initially the rod is at rest. Finally about the rod, angular momentum of center of mass, which is 0 because v2 is passing through the center. Angular momentum about center of mass, which is ml square by 12 omega k cap. L initial is equal to L final, so equate them. mu L by 2 is equal to mv1 L by 2 plus ml square by 12 omega. This is right. But if you take about the point of collision, your life actually becomes more easy. L about point of collision. This is my favorite thing. I always take about point of collision. So up to you though. So let's call it A for the sake of calling it. So L about A is conserved. L initial, L final, the ball, and the rod. Initially, the ball velocity is passing through A. L initial is 0. Final velocity of the ball is also passing through A. 0. Initially, the rod is at rest. 0. Right? The finally rod angular momentum will be m v2 L by 2 minus k cap plus ml square by 12 omega k cap. Since the total angular momentum must be conserved, mv2L must be equal to ml square omega by 12. You get v2 is equal to omega L by 6. You actually get a pretty good result with one single thing. You get a v2 and omega relation with it without capital M and small m. Now, which equation to use? Technically speaking, both are same. You don't get any new equation. If you take this momentum equation and substitute in this equation 3, you'll actually get this equation only. So use any one of them. There is no need to use both. Clear? So this is the preferred point though. Nothing wrong. You can take center of mass or point of collision, but this is the preferred point. These are the 3 steps, everyone. Step 1, conservation of linear momentum. You can't conserve energy because E is not equal to 1. Step 2, coefficient of restitution. Restitution must be about the points of collision ka velocities. Step 3, angular momentum. You got the equations you'll be able to solve. Is this clear, everyone? And the reason why I like the point of collision is for the second question. Find the point on the rod whose velocity is 0 just after collision. You need not even solve the whole thing. So after collision, this guy is going with V2 and this guy is going with omega. If you choose a point somewhere here at a distance x, this will have velocity v2 forward and x omega backward. So you want v2 minus x omega to be 0, but v2 is omega L by 6. Therefore, x is equal to L by 6. And the best thing about this thing, it doesn't depend on the masses, it doesn't depend on the restitution. If the ball hits that end, this is always the case. The point L by 6 will be always at rest. Is this clear, everyone? This is your B part of the equation. All clear with the process? Now I'll give you one more now with some numbers so you guys try. So that's like theory and the concept. We got a rod here, let's say mass is 2m, length L. We have a ball here of mass m going with u. It's the rod somewhere here a distance of L by 4, and let's say E is equal to half. Find velocity of the rod, omega of the rod, and velocity of the ball after collision. There, let's get this. So you're hitting at L by 4, you're not hitting at the end of the rod. Others, do keep your cams on. Right. I'll give a minute or two. We have to do a little work. It is lengthy though. 6u by 5l omega of the rod. Okay. Let's see the rest. U by 5 rod. 6u by 5l. I think omega. Australia the ball is u by 9. Okay. Let's see the equations. Let's check whether you got the equations right. If you got the equations right, then it is just a matter of solving. So draw the rod before and after collision. So after collision, let this guy go with V1, V2, omega. You are interested in this point ka velocity, which is V2 plus omega L by 4. I'm going to take angular momentum about A. Remember, A is a point on the ground, right? It is not a point on the rod, actually. I'm just putting it there. Conservation of linear momentum, mu, mv1 plus 2mv2. U is equal to V1 plus 2V2. Check your equation. Coefficient of restitution, E is equal to V2 plus omega L by 4 minus V1 by initial speed U. This is equal to half. So U by 2 is V2 plus omega L by 4 minus V1. That is your equation 2. I'm going to conserve angular momentum about A. L initial, L final, the ball and the rod. Initially ball is 0 because it is passing through A. Finally ball is 0 because it is passing through A. Rod initially is at rest. Then this way will be mv2 L by 4 minus k cap. In case you're still having problems with calculation of angular momentum, please check out the last class notes. This is what I was saying. Most people have, didn't we do this thing, angular momentum calculation? I taught you the same problem, if you remember. I know this is going to come, so we did it beforehand only. See, this was a 62 problem. I taught you how to cancel angular momentum about B, about A, about C, different points. And for this also I taught you around for the disk about different points. So that is the main thing. You know how to calculate angular momentum. Conservation you can manage. And rod, it is ml square by 12 omega. K cap. So this guy will be V2 is equal to omega L by 3. This is your equation 3. There you got everything. You just dump it there and solve, you'll get the answer. U is V1 plus 2V2. Perfect. Add 1 and 2. Then you get 3u by 2. V1 will get cancelled. Then we'll get 3v2 plus omega L by 4. Take V2 from here and put it here. This will be 3u by 2 is equal to, that will be omega L plus omega L by 4. 5 omega L by 4. Omega will be 6u by 5L. If I got omega, then I'll get V2, which is omega L by 3, which is 2u by 5. If I got V2, I'll get V1 from here. That will be U by 5. Clear? Check your equations. Oh, yeah, got something?
Sir, can you go to the previous slide?
Hmm.
Sir, here, like the I A wheel right? I A into
No. Again, you're messing up. What is angular momentum of the rolling body? Angular momentum of the center of mass plus angular momentum about center of mass. याद है? तो
Yeah,
second
okay.
वाला term will be always same ना? ये देख. If you observe here, ये second वाला term देखा? That will be always same. It doesn't matter about which axis you take. Got it? You will take I about A when if it is hinged here. If it is a pure rotation, you will take our I about A. ठीक है? नहीं, that happens a lot. We generally go for that. So there, angular momentum of center of mass. The second term will be always about center of mass. So it doesn't matter which axis. That rotational stuff will be same. All clear with this thing, everyone? Got this question? Like I said, follow the process, you'll get the answer. There's nothing there. Let's see one more like this. Let's say instead of a particle, we have one more rod, same mass, same length, but it's coming with U. It comes and hits the center and gets stuck. E is equal to 0. So basically it forms an L-shaped rod. Find omega of the system after collision. I could have kept a particle also, but I think you got the process now. So one rod is at rest. This rod comes and hits the end and gets stuck. That becomes an L shape. Find the omega of the system. How do we handle this? Now, where do we conserve angular momentum about? Technically, you can conserve at every point, but now this whole setup will start rotating and moving, right? Things go weirdly. But there is one point who doesn't care about all this. Who is that? the center of mass of the system of both the rods, isn't it? The center of mass of both the rods will continue to go in a straight line, isn't it? So when this thing becomes an L-shaped rod now, the center mass of this and this will be somewhere here. This center mass, this will go in a straight line, and this whole rod will rotate about this axis, isn't it? You can do that. Try, I'll give you a minute more. Hmm. 3u by 4l. Let's see. I don't remember the answer. Let's see. So just before collision, you are going with V. This is there. So your center of mass will be somewhere here, which would be at a distance of L by 4. You can actually just do it in one step, actually, conservation of angular momentum. And after collision, so this would be your center of mass, which is still going with the same velocity, which will be V by 2. Velocity of center of mass will be V by 2. M1 V1 plus M2 V2 by M1 plus M2. So this guy will continue to go in a straight line. And if you look at this whole setup, after some time, this is rotating like this. So after some time, the picture will look like this. The center mass is still here only. The whole setup is rotating, but the center mass is going in a straight line. You can take torque about any axis. So initial, we are doing L about center of mass. Initially, what is the angular moment of center of mass? This is M, that is M. The rod is going in a straight line, so that is MVL by 4 plus angular momentum about center of mass. So VCOM is 0. This will be ICOM omega. So the problem is calculating ICOM. If you take this center and this center, the center of mass will be somewhere here. We actually have to use parallaxes theorem. How much will this distance be? That would be L by 4, L by 2, L by 2, L by root 2 का 2. So this is L by 2 root 2. So when you want to find ICOM, you have to use parallaxes theorem. ML square by 12 plus M L by 2 root 2 whole square into 2 times, because there are 2 rods. Is that clear, everyone? L by 2, L by 2, L by, yeah. That would be ML square by 12 plus ML square by 8. And that will be 1 by 6 plus 1 by 4, 4 plus 6, 10, 10 by 24, 5 ml square by 12. That just looks scary, but it is manageable. Three B by 5L. Or did I goof up somewhere?
No, sir.
Same, no? Anvita, check karo. You got 4, I got 5.
Sir, I got the same thing.
Same, no? Others, can you find any mistake that I did? Or is it fine? Clear what we did? Are you getting why I took about center of mass and not point of collision? You could have taken about point of collision also, it would have worked. But again, you have to do that on angular momentum of system plus angular momentum about center of mass. So about center of mass, your life will be easy. All got this? Let's do a better version of this. We have a rod here, mass 2m, 12. You connected this by a string. Mass m, and you gave speed u. So it can hit the center exactly. This string is length L. This is the top view. Huh? So this entire thing is placed on a smooth floor. So we have a rod of mass 2m and 12. You connected a string to one end of length L, mass m, and you gave speed u. I'll make it m only. It doesn't matter. Okay. So the question, find the tension in the string initially. And let's say if E is 0, find omega after collision. This would be a good one, right? We'll see how you handle this. There's no gravity. Huh? This thing entire setup is on a smooth floor. How to get the tension? That's a good one. Let's see. This will be a good one. Advanced paragraph question. The omega part is easy. That will be the same as the previous one. But that initial tension is a good one. Everyone should try. I'll give you 2 minutes, and others do keep your cams on. Two mu square by 9L. Okay, let's see. I'll give another minute, then I'll show you. One thing, I'm asking you for tension, right? That means you have to draw an FBD. You can't get tension from conservations. I have no idea, Arya. Wait. Let's see. So you want to find tension, draw the FBD. You have done something like this in center of mass. Now, what are the forces acting on this? There is a tension on the rod. But because there's a tension on the rod will also have an acceleration, and the rod will also rotate. So T is equal to MACOM 2M actually. And torque about center of mass will be T into L. Remember, this distance is L. Is equal to I center of mass, which is 2M, 2L whole square by 12 alpha. So that would be 2ml square by 3 alpha. Perfect. And what about the ball? Now, about the ball, you have tension. Now, again, understand this thing. Who thinks it is going in a circle? In the ground frame, it is not going in a circle. In a ground frame, it is going in some weird path. So the person who is standing at this point, let's call him A. So the person at A will think you're going in a circle. So that will be tension T. Since you're going in a circle of radius L, there will be a centrifugal force, which is mu square by L. But don't forget, A himself has acceleration. So you have to apply a pseudo force. That would be m into acceleration of A. Remember, this is your linear pseudo force. We have done the same thing, similar one in center of mass problem. This problem, remember? We did the same steps here. If you're standing at that point, you think it is going in a circle. So there'll be a linear pseudo force and there'll be a centrifugal force. Linear pseudo force. So, but what is the acceleration of A? If you look at the acceleration of A, it has two accelerations now. You're going down with A center of mass and you're going with alpha also. So this point is going with acceleration of A will be A center of mass plus L alpha. Therefore, you get tension plus m into acceleration of A will be mu square by L. But what is acceleration of A? M into ACOM plus ml alpha. ये कल कम हो जाएगा. What is MACOM? T by 2. What is ml alpha? 3T by 2. So that would be 2T, 3T. T is equal to mu square by 3L. Please check. Three T. I think moment of inertia we messed up, right? Mass is 2m, length is 2l, na?
Yes, sir.
भाई
Sir,
अभी
I
बस
took
वही.
2M as M.
हाँ, कुछ तो लिया तूने, बस वही था. Is the calculations clear, everyone? Understood what we did? The question is this. Let me ask you this question. Is this ball going in a circle? Yes or no? It's not going in a circle. If you're standing in the ground frame, the ball is not going in a circle. That means you can't use centrifugal force. If you want to use centrifugal force, first I should see it is going in a circle. And the only person who thinks it is going in a circle, if you stand on this corner. But if you go and stand on that corner, you yourself are accelerating. So we have to apply a linear pseudo force. Is that making sense? All clear with this? Clear, na, Samyak? Ovia, clear with this? Vedika? Yashvi? Shreyan? Then what is the second part of the question? Find omega after collision. So that is kind of easy actually. This is M, this is 2M. Where is the centromass of the system? That will be somewhere here. So the system will go in such a way, the centromass doesn't care. It will always maintain the speed. This is U. So velocity of centromass is U by 3. So after some time, the rod becomes like this. This guy becomes like this. But center of mass will be still somewhere on this line. Eventually, when this thing collides, because it is going to come and collide in the center, the ball will come here and stick. This point only will be the velocity of center of mass. Are you able to visualize the picture? The ball and the rod will go in such a way, the center of mass will continue to go in the same line. This dotted red line is the path of center of mass. And this whole setup is rotating with omega. Conserve angular momentum about center of mass. Since the mass is in the ratio of 2m is to m, this distance will be 12 by 3, and this distance will be L by 3. So that you can figure out perpendicular distances. So initial angular momentum mu 2L by 3. Final angular momentum I of the rod plus I of the ball omega, but I of the ball is 0 because you are at center of mass. The rod will be 2m, 12 whole square by 12 plus 0 omega. Finish this, you'll get the answer. How much is this? When 2 goes off, that will be 3. 3 also goes off. Omega is equal to U by L. U by L. Clear with this? Anita. How did you get 11, Ray? Take look, a happy mistake here. All got this thing. There. So that is few of these questions. So check it out. We did some pretty good questions today. Do resolve them. Next class, when we catch up, we'll continue from here. I think we have another 3-4 problems more. We will wrap up the chapter in the next first half of the class. And after that, we'll start off with fluid mechanics. That will be the next chapter. After this, we'll be doing fluid mechanics and properties of matter. And then we'll go with heat and thermodynamics. Basically, we are following the NCERT 11th ka format. Okay, with that, we'll wrap up for that. We almost hit 79. I think we will cross almost 83, 84. I think this is the biggest so far, I guess. I think kinematics will do even more. But anyways, so do resolve. Start from here. Getting it. There are 79 questions. Covers a lot. You should start solving your material. So yeah, I'll see you guys again on Friday. No, Thursday, same time. So any doubts, anything else, please stay back and ask, or else you're free to leave. And do remember, there's an exam online, so make sure to give before Friday.